Okay, in this video I'd like to show a few things about refraction. Many of you students missed the last few classes for AP tests or park testing, so I thought I would do a simple overview of refraction followed by ways to draw rays through lenses. So first, two analogies. First, imagine you're in a go-kart. So some small car, and maybe you make it with a lawnmower engine or something like that, and you're driving it around in a parking lot or something. And we're looking from above. This is you driving around, and this is a concrete surface. So you're able to go quickly, but you decide to take it off road into the grass, and so over here is the grass. When your go-kart hits this boundary is called an interface. The interface is the boundary between two media. Well, when you hit, the car is not, it's going to slow down as you travel into the grass, but it's not all going to slow down at the same time. Instead, the front right wheel, this one right here, would slow down first, where the front left wheel would still be going quickly. And so as you move into the grass, your go-kart would tend to bend and travel off in this direction. It would go, if I draw in a normal line and I find the angle in and the angle out would be smaller than the angle in. When I'm going fast to slow, it's going to bend closer to the normal. Here's another analogy. This is sometimes referred to as the principle of least time. Pretend you're a lifeguard and you're watching kids swimming in the water at the beach. So here's the beach, and here's the water, and we're looking from above, and here's a swimmer struggling in need of rescue. The lifeguard could choose to take any number of different paths to get to the swimmer. However, if the lifeguard is smart, they'll know that they can run faster on the beach than they can swim in the water. And so, rather than traveling straight through to the swimmer, the lifeguard will take a path that takes them more on the beach and less on the water. In the faster medium, the angle in will be greater than the angle out when measured from the normal. So whether you think about it as a go-kart going into the grass or a lifeguard rescuing a swimmer running farther on the beach so that there's less time in the water, either way we see these kinds of things bending. Well, light does the same thing. But before we get into the bending part of light, we have the concept of speed. So you can see that in both of these analogies, what matters, and the reason for the redirection, is speed. So when we're talking about light, it's important to know the speed of light. So the velocity of light, you've heard the speed of light is often called c. C is the letter given for the speed of light for the Greek word celeritas, which is swift. And in physics, we can figure out the speed of light from this expression, where c is the very fastest speed of light. This is the speed of light in a vacuum. So in the vacuum of space, where there's no material substance for light to travel through, light travels at a blazing fast 300 million meters per second, or 3 times 10 to the 8th. So anytime you see c, you can put 3 times 10 to the 8th. That's the speed of light in a vacuum, the fastest light ever travels. But when light travels through glass or water or diamonds or crystals or plastic, light tends to slow down when entering a new medium. And so, to figure out the speed of light in some new medium, I need to know something about that medium. This number n is called the index of refraction, which is just a number with no units. This index allows us to take one speed and calculate another speed. The speed of light in a vacuum is c, but the speed of light in something else depends on the index of refraction. Here are a few common indices. The index of refraction of a vacuum, obviously, is 1. If I take c divided by 1, I get the speed of light in a vacuum. The index of refraction in air is very close to 1. It's 1.0003. So, for our purposes, this is basically 1. So, in air, index of refraction is basically 1. A common thing we see light travel through is water, so it's helpful to know the index of water. 1.33. So when light goes from air to water, it slows down by this factor. I can determine the speed of light in water by taking 3 times 10 to the 8th divided by 1.33, and I get some number slightly less, 240 or something like that, million meters per second. Another common one is glass. Now there's lots of types of glass. There's just glass from melted quartz, sand, and so on. A typical index of refraction for glass around 1.5, 1.52 I think is common. And so light travels a little slower in glass than water, and a little slower in water than in a vacuum. Either way, this process of bending when light goes from a fast medium to a slow medium is called refraction, and it depends on the index of refraction. There's one other maybe notable index, diamond. If you've ever looked at light emerging from a diamond, you might have noticed it's very rainbowy. A diamond has a very large index of refraction. Light slows down quite a bit going into diamonds. And remember, not only does this cause refraction, but it also causes the dispersion of colors. So I will get a bigger separation between the reds and the violets when looking at light passing through a diamond. So to put it together, refraction, when light travels from, let's say, air to glass, it comes in at some angle perhaps. We always measure that angle from the normal, and we can call this theta 1, the angle in. And whatever this is, it has some index, call it N1. And this glass would have N2. Since light is going from fast to slow, I can predict that the light will emerge closer to the normal on the other side, such that theta 2 is smaller. But if I flip it, and I have a scenario where I have glass and light is now emerging into air, now I have slow to fast. Light comes in at some angle. I measure that angle with respect to the normal. That's theta 1. This is N1, N2. Light now emerges at an angle greater than theta 1. This is theta 2. And this is Snell's law. Snell's law is named after Willibrord Snellius. And I've read that some others actually discovered this before Snell, but in 1641, Willibrord Snellius quantified the relationship between these indices and these angles, and this is it. A fairly elegant expression. So if I know the relative speed of light in two different media, I can predict the change in the angle. So let's do a specific example of this. Let's go air into water this time. Air water. Light ray comes in at some angle. And by the way, if there's no angle, the sign of 0 is 0. And so when you have, this kind of falls down when you have light coming in perpendicular. It just comes out perpendicular. There's no refraction there. We know that this angle can be found. Air has an index of refraction of 1. Water has an index of refraction of 1.33. We anticipate that it'll be smaller, but what angle will it emerge? Let's put some numbers in here. Let's say it comes in at 45 degrees. So, coming over to Snell's law, the index of refraction where the light is coming from is 1. Sine of 45 degrees. The second index is 1.33. Sine of some unknown angle. Now it's important here to make sure if you're using a calculator that your calculator is set to degrees, not radians. And 1 times the sine of 45. The sine of 45 is 0.707. So I can divide this out. And I get 0.53 equals the sine of the angle. But I don't want the sine of the angle, I want the angle. I want theta 2. So how do I get rid of this sine? Well, I can take the sine inverse of both sides of the equation here. So sine inverse, sine to the minus 1. On your calculator, this probably looks like you'd hit like a shift button or a second button and then hit sine, and you'll see that. And here I have the sine inverse of the sine of the angle. Sine inverse, sine, I'm left with just the angle here. And when I take the sine inverse of 0.53, I get 32 degrees. Try that on your calculator. If you get something weird, it's probably because your calculator is in radians. Hit the mode button and make sure your calculator is set to degrees. So this is Snell's law. So Snell's law quantifies how much bending happens. And notice we predicted that 45 in, it would be smaller than 45, and indeed the light emerges at 32 degrees measured from the normal on the other side. So that's Snell's law and refraction.